The last class we have discussed regarding the conditional compilation as well as conditional execution. So today let us discuss regarding useful tasks. So when we are going to consider useful tasks, these are the following tasks we are going to consider. Here the first task what we are considering is file output, and then displaying hierarchy, strobing, random number generation, memory initialization, and then value change dump. Okay, so till now we have discussed five different system tasks. What are those five different system tasks? We have considered the system task as uh, dollar time, which used to display the current simulation time, and then we have used the another system task that is nothing but dollar finish in order to terminate the simulation, and then we have used dollar stop in order to stop, that is pause the simulation operation, and then we have used one more system task that is nothing but we have considered dollar display, okay, in order to display any particular message, and also we have considered one more system task that is nothing but dollar monitor. Okay, so why this dollar monitor was used? We have used this dollar monitor to observe a particular signal. In order to observe a signal change in a particular signal, we have used dollar monitor. And when we consider dollar display, mainly to display a particular string or a particular number, we are going to use dollar display. So like this we had considered five different types of system tasks. Now apart from that, other system tasks that can be used in Verilog coding is file output. So this file output indicates that how we can able to open a file and how we can able to write data inside that file and how to close the file. That file handling will be discussed in file output system task. And similarly, displaying hierarchy, as we discussed in first module, hierarchical level. So when we are going to consider either top down design methodology or bottom up design methodology, there we will going to display in which hierarchy a particular signal or a particular component is present. So that gives the display hierarchy. For example, if I consider a 4-bit ripple carry counter, so in that 4-bit ripple carry counter, to implement it I am using 4 T flip-flops, and to implement each T flip-flop I am using 1 D flip-flop. So like this we are going to consider different components, and each component here, ripple carry counter represents the node, root node, that is nothing but the first level of hierarchy, and T flip flop represents the second level of hierarchy, and similarly the D flip flop will going to represent third level of hierarchy. So like this, in which particular hierarchy a particular component is present, to display that we are going to use display hierarchy. And next what we are having is strobing. So when we are going to consider dollar display, it will going to display the message, but depends on the simulator when whether it will going to display the content first and after the modification of a particular value, or before modification of a particular value whether it will going to display. So like this the execution of dollar display is not proper, means we cannot determine exactly when the dollar display will going to display a message. But when I'm going to consider strobing, what this strobing will going to do, it will going to wait until all the signals are updated and later it will going to display at the end. Okay, that is why we are going to call it as strobing. And next what we are having is random number generation. whenever we want to generate a particular random number. Why actually random numbers are useful? Because when we want to test any particular device, in that case some randomly generated inputs are provided, so that if we give some randomly generated input to test the functionality of a particular object or a particular device, in that case we will going to get the output, and based on the output we can observe that whether we are getting proper output or not. Means sometimes for a particular input we may get proper output, but not for all the inputs. So when we give inputs randomly, it will going to check all different possible ways, type of giving the output. There we can able to check the functionality. For example, we had considered 4-bit binary to gray code conversion, isn't it? So in that 4-bit binary to gray code conversion, what we did, we gave the input which we know, and only one or two inputs we gave, and we observed whether we are getting correct output or not. We did not check for all the inputs. If I take 4-bit binary to gray conversion, then totally there will be 16 different combination. And apart from 0 and 1, if you are able to get the input value as X as well as high impedance, in that case, what is the output? That also we have not observed, isn't it? But when we generate a number randomly, there uh, checking the error or debugging the error present in the device circuit design will be more easy. Okay, and also it represents that we have checked for almost all possible combinations. So like this, the quality of the circuit will be tested by giving random inputs. In order to give random inputs, we have to consider random number generator. For example, if I have built a multiplier circuit, then I have to check whether the multiplier circuit will going to work for all type of data. Okay, for all the data. But when I consider a 32-bit integer, how many number integers I can get? 0 to 2 raised to 32. That many number of integers I can get. I cannot able to check for each and every data. If the data size is small, then I can able to give each and every value and I can check the functionality. But if the data size is large, then checking by giving each and every value will be difficult. So in such case, I'll select randomly a particular number and I'm going to check whether I'm getting proper output or not. So like this, we can able to check the functionality using the random numbers. And afterwards, what we are having is memory initialization. Memory initialization means we are having some bytes of memory, and for that bytes we have to read data from the file present in the device, and that should be loaded. So loading the memory with the some pre or initial value is known as memory initialization. Before utilizing the memory, we want to load some data for the memory and then it has to be utilized. So in order to load data for the memory, we are going to do memory initialization. And next, what we are having is value change dump. This value change dump we are already using in the lab, where you are going to use $dump file, and also we are going to use $dump vars, isn't it? So why, how this particular $dump system task will going to work, all these things we are going to study in this particular section. Okay, so first let us consider file output. When I'm going to consider the file output, so here mainly three operations we are going to consider: opening a file, writing data to a file, and then closing the file. Usually whenever we are going to execute any program, the output will be written in standard log file. So when the corresponding file has been opened, what data has been written, and when the file has been closed, that is considered standard log file. In that log file, we will be having the corresponding data, output data, but that cannot be read or modified by the user. So what user will going to do, if he want to save a particular results in a file, then he can only create a file. In that created file, he can write the data and he can close the file. Whenever he want, he can able to access the file. All the time he cannot able to access the standard output file, that is nothing but verilog.log. But when the data is saved, in that case he can able to check whether he is written data in a proper whether he is getting output in a proper manner or not. All these things he can able to check when he can able to write data in a particular file. Okay, so first let us consider file opening. Okay, we have to mention $f open, and then we have to mention the name of the file which we want to open. So when I mention $file and name of the file, in that case, in which directory the software is executing, in that directory a name, a particular file will be present, and that can be opened, because before writing I need to open the file, so it will going to open the file. When once the file is opened, it will be remembered in the name of channel descriptor. Okay, so the general log file, that is the standard output file, will be considered as channel 0, which the designer or user cannot access. And apart from that, if we open any other file, then it is considered represented by the file handle, and this file handle will be of 32-bit data. Means 32-bit means it is an integer. Every file will be remembered by the integer. Like how we are going to remember the student data based on the USN, in the same way we are going to remember the file using the channel number, and this channel number is of 32-bit. So every every file will be represented by a bit. If a first file is opened, then the first bit will be set. If anyway, standard output bit will be considered in the 0th bit. Okay, always 0th bit will be set to high. And when I open, apart from the standard file, if I open any other file, it will be set, the next higher bit will be set. Suppose if I open one more file, then the second bit will be set. So if I open up around 30 files, all the upper 30 bits will be set. So up to 30 files we can open, and the last bit is reserved, that we cannot use as a file handle. Okay, and each bit will be representing a particular channel descriptor, and based on this particular bit, if the first bit is set, then whatever the data we are going to write, it will be written in the first file. And when a second bit is set, then whatever the data we are going to write, it will be written in second file. Okay, if two bits are set, okay, in that case, while writing the data, if two bits are set, then the data will be written in both first file as well as second file. Like this, it will going to write based on which particular channel bit has been set. So always remember, whenever we open a file handle while writing, first, to open a file, we are going to use $f open. Using this, I am going to open the file. But that file should be assigned with a corresponding file handle. That file handle is a 32-bit channel descriptor. Okay. So always we have to declare an integer to consider as a channel descriptor. And depending upon the number of files opened, the corresponding bits in the channel descriptor will be set. Okay, that let us consider an example. So here first we will going to declare the file handle, because we should know for which particular variable the file handle 32-bit has to be saved. So for that, first only I'll declare, if I want to open 3 files, I'll going to declare 3 file handles, or if I want to open only 1 file, then I'm going to declare only 1 file handle. So why I have given the name handle 1, handle 2, so that it can be easily remembered. It belongs to the file handling channel descriptor. And since it is a 32-bit, I'm going to consider it as a integer. And now we are going to consider the standard output is open. So as soon as we consider this channel descriptor, the log file will be created, because it has to mention when the corresponding file has been, log file has been opened, and what data has been written, and when it has been closed. All these things will be logged, means it will be accounted in the standard IO file, okay, log file. But apart from that, when we are opening any other files, then we have to write the corresponding file handle. So here you can see handle 1, within the initial statement I have written handle 1 is equal to $f open file dot out. So file 1 is the name of the file. This dot out indicates that it is a output file. Okay, so do not consider dot text or dot some dat like this. It should be an output file. Since it is a log file, we are writing program for the log file. We have to consider with an extension dot out. And here I'm going to give name, and then I'm going to mention f open, $f open file1 dot out. In a particular directory, it will open a file. Since this is the first file it has been opened, the first bit will be set. Okay, so why the name, the number 2 has been considered is, see, when I'm going to consider the 32-bit, so all the upper bits will be 0, and then the LSB bit, it is set for the channel descriptor, but for the first file descriptor, it has to consider only first bit, not the LSB bit. So according to this, the file handle number for the first file is 2. Similarly, for the second file, the corresponding number is, it has to consider second bit as set, not the other bits. So as a result, the number for the second file handle is 4. So like this, it will going to give the corresponding bits. Only here in the bracket I have mentioned, the first bit is set. Out of 32 bits, only first bit is set. And here out of 32 bits, only second bit is set. 0th bit is for the standard output. So here you can see only 0th bit is set. But for the file where the designer wants to create a log file, there we can use the bits from first to 30. Okay, so like this, how many number of files I am going to open, that many number of handles I have to mention. And each file handle must be an integer of 32-bit. So this is how we can able to open a file. The next thing is, I want to write data for a file. So in order to write data for a file, we are going to use either $f display or $f monitor. So what this $f display or $f monitor will going to do, as we seen in the Verilog program, if I mention $f display in the console, it will display the output, isn't it? Means it is writing data to the console. where it is a standard log file. In the same way, when I open a file and if I write $f display, then it will write the data in the file which has been opened. So this is the general syntax what we are going to consider. $f display, within parenthesis we have to mention for which descriptor we have to write and what data we have to write. This data can be any variable or any signal name or any string within double quotes. So like this we can able to write the data. And here the descriptor. What descriptor we have to consider? Instead of giving the descriptor as 02, I'll give the descriptor as handle 1, because the descriptor value is stored in this particular variable. So here I'll be mentioning $f display. F represents file. So in this file it has to display, and then I'll mention the descriptor and I'll do. And here you can observe that the syntax of $display and $monitor is same compared to the $f display and $f monitor. The only change what we are going to consider is here the first part will be representing the file descriptor. After that, we are going to write the content which has to be displayed in the file. Okay, but in case of $display, we will not be having file descriptor. We will be having only the content which has to be displayed on the standard log file. Okay, this is how we can able to write the data in any particular output file. And next, what we are having is an example how to write data. So in this, I have considered 3 integers, the DESC1, descriptor 1, descriptor 2, and descriptor 3. Okay. Why I have taken this integer means, if I use only the handle 1 as a descriptor, in that case, it will write file only for the first file. And if I consider this as DESC equals handle 1 or 1. So or 1 means here I am considering LSB bit has been set. So what it will do? It will write the data in both standard log file as well as in the file number 1. And similarly, here what I am doing is file for descriptor 2, I am considering handle 2 or handle 1. So handle 2, in that handle 2, the value 4 is present, and in the handle 1, the value 2 is present. So 2 or with 4 means I'll be getting 6. So what I'm going to do here, I'm writing $f display descriptor 2, that is DESC2, comma display 2. So this message will be written in both file 1 as well as file 2. And here I am not considering any other file. Only for handle 3 I want to write. Either I can directly mention handle 3 here, or by using this descriptor I can mention. So here this display will be written only on the file number 3. Like this we can able to write data for either one file or more than one file. If you want to write data for more than one file, then which are all the files, for which files we want to write data commonly, all those file handle bits should be ORed in the descriptor, and then it has to be given inside $display. Okay. And after this, we want to close the file. After writing the program, after displaying the message, the particular file has to be closed. So in order to close the file, we are going to use $f close, the keyword $f close, and then handle number in which particular file I want to close. So like this, I can able to open the file, then write data to the file, and then I can able to close the file. So for this, let us consider a programming example. I'll just share the screen. So here we can able to see the program. In this program, what I have done is I have declared a module by name file underscore OPR. There is no input output ports for this file, and I have declared the integers. Three integers as handle 1, handle 2, handle 3. Similarly, another three integers descriptor 1, descriptor 2 and descriptor 3. Okay. And whenever we write this particular any particular module, if we define, standard log file will going to open by default. We need not necessary to open the standard log file. By default it will open. Means when we define any module, after defining we will going to see whether the module is correct or not. Everything will be observed in the console, isn't it? Here after writing the program, when we do check syntax, again the corresponding result will be done in the shown in the log file, what we have done and what is the corresponding response. So that is why we need not necessary to open the file standard file handle. And now I'm going to consider the same statements, that is handle 1 is equal to f open, that is file1 dot out. So here in which directory it is present, the same directory I have to open. So let me show this. In this directory we can able to see three files by name file1, file2, file3. Here you can observe file1, file2 and file3. So when we observe these files, so if I just double click on this, I can able to see this particular data has been already stored. So first I'll just delete whatever the data is present in this, because we want to see the demo, how we are going to get the output. Okay, so I'll just delete all these things. And one more, file 3 here. So file 1, file 2 and then file 3. So here we can observe that all the files are empty. And now what we have to do is we are going to consider this statement. And afterwards, after opening the file, we are considering write data. So here the descriptor, as I told, we are going to consider the handle 1 or with standard log file. So this value display message in file 1 and standard IO. It has to be displayed in console as well as in the first file. And display message in file 1 and file 2. This message has to be displayed in the first file as well as second file, because I am performing OR operation. So both the bits are set in the channel descriptor. As both the bits are set, the data will be returned to both the files. Okay. And in the third one, only one particular file handle I have taken. And next, after writing the data, we are writing close the corresponding files, file 1, file 2 and file 3. So now let us simulate this particular. So here we are considering this file operator, and then after checking the syntax, go for simulation. So when we simulate, here you can see in the console which particular message has been displayed. Message, display message in file 1 and stdio. Because for the descriptor, in the first descriptor, I had mentioned it has to display in first file and standard IO. But in these two descriptor 2 and descriptor 3, I have not considered standard IO. So it is not displayed in the console. Only the first message has been displayed in the console. Now let us see the corresponding files. File number 1. I'll just close these files and reopen so that we can able to observe. So file 1. So now see, when we reopen, we can able to see the first message, that is according to the program, this message should be also written in handle 1, that is display message in file 1 and stdio. And also the second message, because the handle 1 is present in two descriptors. So as a result, it has to write two files. First, this statement is executed and then this statement is executed. In the same order, you can able to see display message 1 in file 1 and stdio and display message in file 1 and file 2. Okay, now let us observe whether the data is present in file 2. And only second descriptor is having file 2, so the second message is displayed in file 2. Similarly, when I am going to consider the third descriptor, here we can able to observe that this message should be displayed in file 3, and in the third descriptor I have written only this message. So like this, whichever the data we want to write, that can be written in the file using $display. Okay, so this is one of the example how to write file using $display. And next, what we are having is, we have observed opening of a file, writing a data to a file, and then closing of a file. Next, what we are having is display hierarchy. If I want to find out in which particular hierarchy the corresponding instance is present, in that case I am going to use %m. So while discussing in module 2, I have mentioned this example. In the same ripple carry counter, to display the hierarchy level, we have considered %m. Here also we are going to consider %m in $display. $f display is different and $display is different. $f display will display the data in file, and $display will display the data only in standard log file. It will not going to display in any other file. Okay. So here in the main module, we will going to write the program display in %m. Okay. And then whenever this particular module m is instantiated in any other modules, then this hierarchy will be keep on displaying. Okay. So here we can see the output, like in this example, I have taken the instance m with the instance name m1 as well as m2, and previously I took m3 also. So that is why I am getting the output like it present in the root module is top. Inside the root module, it is present in the first hierarchy, that is m1. And similarly, m2 is also present in the first hierarchy and m3 is also present in the first hierarchy. Like this, we are going to get the output by using display hierarchy. Okay, so here I have considered some example for that in order to display the hierarchy. Yeah. So here we are having a ripple carry counter. So in this ripple carry counter, what we are having is, we have instantiated T flip-flop, and inside this T flip-flop, we have instantiated D flip-flop, and inside this D flip-flop, I have mentioned this D flip-flop is present in %m level of hierarchy. So what this has to do? It has to display in which hierarchy the D flip-flop is present in the stimulus program, because stimulus program has instantiated ripple carry counter, and ripple carry counter has instantiated T flip-flop, and T flip-flop has instantiated D flip-flop. So now let us observe the output, how it will going to display the corresponding hierarchy level. So whichever the module you want to find its hierarchy, you can able to consider this. 1 minute. Why it is not displaying? Oh, sorry, I have comment. No, it's not commented. Yeah. So here in this, the top module in which the D flip-flop instantiated is ripple carry counter. Inside this ripple carry counter, we are considering T flip-flop, and inside this T flip-flop, the D flip-flop is present. So that is why it has been displayed. In all the 4 T flip-flops, D flip-flop is instantiated. So here you can see the corresponding instance name. So while displaying the hierarchy, we have to follow. The first module is ripple carry counter. Below that, T flip-flop. And the third level is D flip-flop. So this dot separates the corresponding hierarchy level. So if I mention the same message inside the T flip-flop, so what happens is, here, whatever the message I have placed inside the T flip-flop, if I also mention the same in the D flip-flop, I can able to see it will display both the hierarchy levels, the T flip-flop hierarchy level as well as D flip-flop hierarchy level. Yeah, here you can observe the D flip-flop is present in ripple carry counter, inside the T flip-flop, inside the DFF. So here, oh sorry, I have not changed the name. So since I copied the same thing, here it is showing the corresponding hierarchy of T flip-flop. Like this, we can able to find the hierarchy using display message. Okay. And next, what we are considering is strobing. So when we are going to consider strobing, it is similar to dollar display. The only thing is we cannot able to predict when dollar display will going to execute. But when I'm going to consider strobing, it will always execute after all assignment statements in the same time. As I told, these data or these statements should be written inside always or initial block. So as a result, what happens is always and initial block or concurrent statement, but statement inside the always and initial block are sequential. So what it has to do? First, it will execute all the statement, means the values on the RHS side of the statement are computed, but assignment will be done before exiting the corresponding always or initial block. In that case, what it will going to do? Either this statement assignment may be done first, or this statement assignment may be done first. We cannot predict. Calculation has been done in a sequential order, but assigning the value will be done at the end. Okay, while assigning, we cannot predict the order. In the same thing, if I use dollar display, there also I cannot predict in which order dollar display will going to execute. So as a result, here I cannot tell whether before updating the value dollar display has been assigned or shown the value in the log file, or after assigning the value it is showing the value in log file. That we cannot predict. But if I use $strobe, then it always ensures that after completing all the assignment, at the end it will going to execute. So basically, when we are going to consider synchronous circuit, there we are going to use $strobe, because everything should be synchronous with respect to a particular operation. So here the $strobe, as it executes at the end, then all the previous tasks or executions will be completed, then only it will display. Till then it will not going to display. Like this we can get synchronization mechanism. And in small programs we cannot able to identify the difference between $display and $strobe. But when we go for the larger program, like if we are designing a microcontroller or microprocessor circuits, there the code of the circuit will be large. Intermediate values or intermediate signals or alarms has to be displayed, warnings. In such case we can consider $strobe as well as $display.